Hi, everyone. I'm Vinod. I serve as the PMC chair for the Apache Hudi project, which adds transactions, updates, and deletes to data lakes. And I also recently founded a company in the space. Today, we'll discuss lakes, lake houses, warehouses, all types of lakes and houses in this talk. And our goal is we'll do our bit to put them into perspective by kind of comparing and contrasting them side by side. To kick it off, a brief overview of my background. And in the past, I've mostly worked on distributed systems and databases. I started my career at Oracle, working on the Oracle database server, transaction manager, CDC, change capture, and then I led the Voldemort key value store project while I was at LinkedIn. And I had a brief stint at Box where I was building another data store, which is proprietary. And then I moved on to Uber actually, where Hudi happened. I also Hudi is the first, the earliest Lakehouse tech. I simply built it way back at Uber to solve our data lake transactional needs. And then most recently, before OneHouse, I was at Confluent working on KSQL, on streaming database Kafka, and many other things. So for today, we'll first sketch the arc of evolution of these different data infrastructure systems around warehouses and lakes and lake houses. And we'll contrast them across these three different kind of like areas. And I'll just leave you with a parting thought on like an alternate model that we've seen many companies adopt in open source through, in the 4 or 5 years of supporting the open source Hudi community. So if you go back like 20 years, all we had was on-prem data warehouses, right? You can think of on-prem data warehouses as specialized databases for analytics. That's pretty simple. That's all we had at first. Data lakes, on the other hand, where they came up during the search, the social network era, where lots of information was being collected, and they were mostly intended as an architectural pattern, not a tangible piece of software like an RDBMS or a warehouse, right? But steadily, lots of innovation has happened on both sides. You got BigQuery, pioneering a serverless model for cloud warehouses, hiding all the complexity. You just write a query and you get responses back. Then Redshift actually, in my opinion, took cloud warehouses prime time. They had a really successful product, which went to end with the manageability. Really, took this mainstream. I would say the warehouses to the cloud. And Snowflake, obviously, is a very famous example where they decouple the storage and the compute aspects of the warehouse, coupled with great usability, which gave them a lot of flexibility for the users. And that's kind of like the where cloud warehousing stands right now. And if you sketch the evolution of the data lake technologies, pretty much Apache Spark is what revolutionized data lakes, I would say, data processing, moving away from MapReduce to a more general purpose DAG, which even unlocked for us the ability to build things like Hudi back at Uber. So we thought of, when we built Hudi at Uber, we thought of Hudi as a transactional layer that adds some of the warehousing capabilities back onto the lake. That way we can leverage the scale and the cost effectiveness and the for data science and other large scale workloads, while at the same time we can have these like new cool transactional capabilities, updates, indexes, and whatnot. And as you know, like Databricks Delta as a product came out after that, and what's now been pushed as a evolved to a point where it's been pushed as a Lakehouse architecture, and this is kind of like where we'll spend most of our time and trying to understand and contrast these two things. So I just also want to just briefly introduce Hudi here as well, just so everybody can understand where my perspectives come from. Hudi started at its core as a database kernel, if you will, right? Like, going all the way back, we had like an on-prem warehouse that could, do support transactions, take in merges, updates, but we couldn't really scale it. So we added, transactions, indexes, upserts, deletes, and change capture, typically stuff that you'll find in databases on top of lakes. That's how Hudi started. But steadily over the last few years, we've added a complete set of services that go beyond a basic table format that you have and unlock actually self-managed data lakes at scale, which means that you can just take Hudi and all these platform components and you'll be able to build, run your own data lake, which is all managed. The file sizing is done. It can cluster data. Like there's all these different services. It can track it has an internal metadata table where it can track file listings to scale your cloud, file storage listings, column stats, indexing, z ordering, any kind of like it's a complete data managed data plane for your lake. That's kind of like how the project has evolved at this point. And to quickly touch upon some core differentiators, Hudi makes a bunch of subtle, very deep design trade-offs around concurrency, layouts, metadata that make it like the best suited and the most optimized technical choice out there for incremental processing, which means if you want to quickly ingest data or if you want to write the ETL jobs which run much, much faster than your batch jobs, those are all things that Hudi can do very well on top of your regular, sort of batch workload and scaling metadata for very large shapes. And overall, I think Lakehouse as a technology shift away from just having lakes is pretty much validated at this point. We've seen actually very, you can see these are some very common daily services and deeper enterprises combined, which have adopted Hudi. And you can find, for example, TikTok usage is like over an exabyte of data is what they have managed daily on Hudi. And um, Hudi can be used with Trino as well. Actually, there's a ton of Hudi Trino users, including the good folks at Robinhood, who built like a near real-time data lake on top of Trino and Hudi. And essentially, you combine fast data, from Hudi with fast queries from Trino, and then as you can imagine, a company like Robinhood has a lot of transactional data sources and a lot of things happening in real time. Hudi in Trino can unlock a lot. And there's actually some history here on Trino and Hudi. The support that you find today for Hudi inside Trino is actually dates back to the support grandfather from the Presto days. So and we're doing a lot of work around adding a new Hudi connector, which can bring the latest and the greatest of Hudi to Trino users. So if you're interested in doing this more, please go upload this PR out there and then help us, kind of like we'll be happy to work with you and get this, landed for the community. And if you want to check out Hudi more, you can go to hudi.apache.org. With that context, now, let's get back on the horse. So first, we'll look at, the warehousing architecture, right? How does it really compare? While it's hard to exactly know the internal nitty-gritty of closed systems, high level, all on-prem warehouses operate like a cluster of nodes, and they're all vertically scaled. And there is limited horizontal scaling, meaning you cannot have thousands of nodes in a cluster or hundreds of nodes even for most part, but you buy beefier boxes and the SQL engine, the optimizer, everything is optimized in C++, to run and squeeze the performance out of each core that you buy. And on high level, you had local storage. All data gets stored in this, like tens of like cluster nodes, and all SQL runs on the same boxes. So pretty much you can't scale storage and compute independently of each other. And this is the biggest thing that modern cloud warehouses kind of changed. And what they did was they pulled out some of the core components, like tracking metadata for all the tables, or transaction management, locks, and even SQL optimizer, for example, into platform services on the cloud, which are always running. And then users data is primarily stored in cloud storage, and you bring up on-demand warehouses which can now locally cache that part of the data that's needed for your query execution. This way, what fundamentally the great large benefit was for all those users who weren't able to scale their warehousing needs. The cloud storage provided infinite elastic scaling of storage, and then this decoupling of platform services and having being able to spin up different compute virtual warehouses meant that you could actually have a lot of flexibility in how share the same data across different teams. You don't have to copy data around now. And you have with cloud, you have on-demand pricing. This pretty much has revolutionized the warehousing as we know it in the last 10 years. So now moving on to lake houses and lakes, right? So interestingly, data lakes were always decoupled storage and compute. This is not new, right? Even when we had HDFS and Hive, I mean, that's how it was. The storage was decoupled from compute, and even like Presto on HDFS, for example, that's how people run. They'll always been like that. So high level, you have cloud storage or HDFS or something, and then you have a collection of files, and then you spin up nodes. Depending on the engine, you have a local cache or not, but pretty much you then run SQL on top of, or write code on top of these query engine frameworks that just access data on storage. With lakehouses, what we've primarily done is we introduced a layer in between now, which has three components. One is a table format, meaning like it essentially says what's a schema, track some metadata about the table. Like famously, Hive Metastore, for example, only tracks metadata at the partition level, right? You need something to track metadata at the column and the file level, then that sort of granular metadata you can track. Then all these services that we just discussed when I was showing Hudi, right? The clustering service or like an ingest service, all these different services. And then some like transaction management layer, which can now take multiple writers, multiple readers, and they can access a given table sort of like correctly and transactionally. That's pretty much what's happened. And this essentially means that it's blurring the lines now between how the cloud warehouses look and how lakes look, right? So moving on slightly to openness. I mean, like you might have heard if you just Google and read even warehouses, lakes or something, the thing that pops in people's head is open. Oh, yeah, lakes are more open, right? But there's more to it actually when you consider openness. There are many facets to this. Let's go one by one, and we see that okay, for most part, what people will say is, oh, you have an open format. What it really buys you is it's interoperable in a sense that, well, I mean, you don't have to wait for a vendor to add support. You can write your own job or something, you can access the data if you want. For example, with warehouses, they have external tables, but pretty much the vendors control and they pick and choose based on their business priorities what formats to support and what formats not to support, because for the most part they compete with their own internal formats as well, right? So open formats really give you this like level playing field where everybody can build integrations, and there's more competition leads to like better products overall, right? But lakehouses actually have open file and table formats as the basis for most of what we do. And even with warehouses, interoperability is a different thing, where interoperability actually varies based on how popular a warehouse is, right? Like if there's a very popular warehouse, a lot of people will interoperate with it anyway. So this good to kind of like tease apart the openness aspect and the interoperability. Moving on, like data location and access. Warehouses, mostly the data is stored with the vendor and they're internally managed by it, right? And you can or cannot access the data across accounts depending on the warehouse. Most of the lakes, the data lives with you in your bucket, and you can actually, let's say, it's very easy for you, it's effective for you to access the data within your own account by, you can write a raw Spark job, which can hit data in your own bucket very effectively without paying any network costs or things like that. The data services. So here is where the key difference is. And mostly formats are like a means to an end, at least coming from a very database background that I have. Like you don't find, for example, MySQL, Postgres, and like Oracle and like SQL Server agreeing on a format, right? They usually provide a same standard interface and standard set of like services on top, database services, and then hide the format. uh, that's how warehouses are built, right? They hide all the details and expose a bunch of services that you use to interact with the warehouse. With the lakes, they actually expose the format. Everybody makes the format kind of like open. But then what vendors in the space do is they then like build a lot of services that are locked to each vendor. And if you ask me one USP for the Apache Hudi project, this is what we tried to do from the start is we have built a lot of open services that are typically locked to vendors right in open source. That way you don't not just get the format, but you can actually take these services and run them yourself as well. That is what will unlock true freedom. If you're really looking for like a no lock-in solution, you need both open formats and open services, right? The last aspect is code and community. This kind of controls how much roadmap influence you have. If you have a large engineering team, can you make contributions to this project, right? So and warehouses are proprietary code bases, as you know. And then even if you're a large enterprise with 30, 40 engineers who can actually write this code, you can't really do much, right? You're tied to the vendor roadmap. Even on the lake space, since it's all like a lot of these formats are open, you can actually go and contribute to the projects which have like a more diverse grassroots open source projects. You'll also find some projects are more controlled by vendors, but by and large, you should be able to contribute to these open source projects, even if not, kind of like influence the roadmap. But let's say for the Apache governed projects, there's very strict governance models around how the project is even roadmapped. So you should be able to go in there with your team and influence the project if you want to, right? So just to summarize, warehouses are really built for BI. And you might have heard this, said many times, but what does it mean? They're actually built for scanning the least amount of data possible. That's the BI problem. When you're writing a BI query, you want to return very quickly, scanning the least amount of data, right? So warehouses have performant metadata. Remember, they store metadata as platform services. Like for example, BigQuery or Snowflake would use NoSQL, stores and like horizontal key value stores to store this kind of information. And then they have long running servers for better management. So they're really built for, they can cache a lot of metadata, a lot of different things that is in the query path, and they are like optimized for this. Lakes can support scalable AI, ML, data science, however, data engineering, however you want to like look at it. Pretty much means that they can scan vast amounts of data very efficiently, which means direct access to cloud storage. There's no intermediate service involved, and they have a rich support for different data frameworks, and it can grow faster because there's like open formats. Lakehouses are trying to blend both, but in my opinion, there's still like technical challenges we need to solve. We need like much faster query planning and execution still. And unstructured data is still WIP, right? The other thing that you'll find is when you talk about lakes and warehouses, people say lakes unstructured, warehouses structured. Lakehouses at this point are pretty much structured. There's a lot more work we need to do around unstructured data here. So quickly moving on to just like core reading, writing capabilities, right? So at this point, if you take all the Lakehouse libraries on one hand and compare them with managed cloud warehouses, right? Because that's usually where the conversation is. Actually, updates, transactions, data skipping, sorting, all of these things are like commonly supported by both sides. And what you will find is cloud warehouses support more databasey, multi-table transactions, material use, these kind of more databasey concepts and like implementations. While on the Lakehouse, you will actually find some specific features which are, built for high-scale data on the lake. Like, for example, like Hudi supports primary keys. So that we can do lakes CDC to the lake a lot more. Both Hudi, Delta Lake, in the the proprietary version, they support Z-order space curves, which we have in open source. And something like Hudi is really optimized for streaming updates, which is pretty much changed our ingestion model on the lake from batch to kind of like incremental / streaming. So you'll find some specific use cases which warehouses don't have because they typically don't operate at the data scale that the lakes do. And now this is the interesting part, right? Now you come back to the data services that I talk about. If you look at cloud warehouses, there'll be like fully managed services around sorting, clustering. You don't ever see the files, right? They size it automatically internally for you. Caching is transparent, space reclamation, all of these things are like fully managed. The table, like you don't have to worry about it, right? In terms of Lakehouse Libs, again, going back to why even I'm bringing this up, this has been a core, goal for the Hudi project from the day one, which is we realized that when we started on it, oh, there are all these formats and engines, but there is virtually no management of the tables that you can find. So something like Hudi has automatic self-managed capabilities for almost all of them, but it's a library. You still need to take Hudi and then you need to build your pipeline. You need to configure it and tune it and make it happen, right? And then Delta Lake, for example, exposes a lot of some of these things as commands for you to run if you want, but you're still responsible for like figuring out what command to run and when and schedule and make sure it's actually applied correctly and all of that. That operational overhead is on you, right? And the caching on the lake, it's like vendor specific. Each engine has its own cache. And sometimes if you globally think about it, if you're using 3 engines, then yeah, you're caching it thrice, right? So that's another thing to consider. And moving on, I think there are also other services, right, which are not related to a table storage, but it's more around how do you even get data in? How do you do this other background businessy things like masking, some sort of things like that? So yeah, so for Hudi, we've actually built out a lot of ingestion capabilities. There's a built-in ingest tool, but it's still DIY in a sense that it's self-managed. You need to take the library, learn the tool, run it, but then it can do Debezium, Hudi, end to end. You can pull data from Kafka and all of this. Cloud warehouses, since they're managed services, they offer you, zero ops managed services for some of these things already, right? So moving on to price performance. So this is more nuanced, right? And then most people, when they say performance, they immediately start thinking about, okay, I saw this TPCDS benchmark, right? But it's more nuanced because there are different workloads here that you do. There's ingest workloads. There's all this management workload around backfilling, reprocessing. I want to delete some data for GDPR, file sizing, tuning, repartition, all these things. And then you actually write the ETLs. You join a bunch of things and then you derive new tables. Then you query them, right? So the main thing you need to think about is, do all of this need a premium engine, right? Some of these, the premium in the engines are typically around SQL optimizers and caching and that sort of thing, right? And a lot of these things don't need that. So different workloads have different price performance. And something generally for you to think about is, like, is one engine the right choice for everything, right? So with that context, now let's go back to the thing that we usually have read and understood, the famous TPCDS wars, right? So let's take a single query and then see how the stages in that query and how kind of Lakehouse, like how these technologies stack up. So if you take a query, you first fetch the metadata. It's like, do these columns exist in the table? What's the table schema? Okay, these where clauses, general, all the different metadata about the table, right? So Lakehouses store these on flat files. Some Delta Lake has like some JSON files. If you look at Iceberg, it has like some Avro file for this thing. And we at Hudi, we use like a indexed H file for this. It's either in flat files or some Hive metastore. Warehouses use these statistics in like databases, and a CS101 class will tell you, what's faster, right? So statistics collections, this part, I think we need, it's the early days in the Lakehouse. I think for very large tables with lots of files, I think Lakehouses still need to be optimized. So next you come to query planning, which is, well, now I've figured out my data. I know the files that I need to read, but given 5 tables like that, how do I now plan the query? Which do I join first? And how do I, what's my execution tree, all those things? It depends on the engine and the vendor, right? And then here, there are, even within the lake, there are like very different trade-offs. If you just take Trino and Spark, for example, Trino is like really optimized for fast responses, streaming model execution. So it's really great for interactive analytics. And if you take Spark will spill to disk on failures and it can be more resilient for data pipelines, right? And warehouses, on paper, I think if you think about it, these are very hard problems to solve in computer science. So you would imagine that whoever's been at it the longer usually has the better optimizer. Of course, assuming they all have the same kind of team on it, right? So just look at the RDBMS. The optimizers were written for decades, right, in Oracle or SQL Server or any of these things. And finally, the execution of the query, right? Which is where I think reading of the file format, where the actual, the file format, how well it's written, all of this come in. Lakehouse is mostly, they work on open file formats like Parquet or ORC. Warehouses have their internal formats, but I, I don't think the difference really is in the file format. It's more in the query planning and the statistics layer is where you see the query differences between them, right? And I mean, just to close this topic off, right? I mean, it's a kind of like an uninspiring answer, but TPCDA is great, but really what's better really depends on your workload. And the one piece of advice I'll have is like always benchmark on some real workloads. TPCDA is great, but doesn't mean that you actually have a representative work, like your mix is like that, right? And if you simply look at this, right, this table, you can see that from the barebone EC2 cost, that is essentially, at least on the lake, you can take any engine and run it on your own. And then you get a lot of management and a lot of different performance features on top of this from different vendors. So you have different price performance for your workloads. So you can actually save a lot by being more judicious and benchmark on your real workloads and actually find out where you need to send what workload, right? And the other thing is it's kind of a little bit counterintuitive, but should everything need to be fast? If your team can actually, let's say you have a job that runs once a day, let's say three times a day. If you can afford to wait maybe 15 minutes more, maybe you can drop your cost by a lot. If that's the case, then you want to consider these things more carefully, right? The main thing I've always been surprised about in this space was there is really no benchmarks around ETL workloads. Everybody talks about TPCDS. And if you look at organizations, they spend lots of dollars on ETL workloads, costing significant amount of money. And then from the Hudi community, again, we've seen tons and tons of organizations that I showed before who've done these kinds of CDC workloads into the lake. And these workload patterns really don't line up with TPCDS or anything that we've done. So we need some more standardization, some better benchmarks for this, right? And finally, these data optimizations really do matter. If you take Hudi or all this C ordering, clustering, all these different things, they make a large impact to your performance. So you should think about how you more than also the engine, how you can control the storage layout. For example, clustering can improve performance, and space curves can fundamentally as well change the layout and help you do more high dimensional data. It can actually help you get better query performance out of it too, right? So in summary, warehouses are more closed systems. Lakehouses are open depending on, but you need to think through what exactly is open and how you can influence and how you can take advantage of that, right? And they're built for BI. Lakehouses are better ML, DS, AI support. They're fully managed for the most part. You have to actually build lakehouses or lakes, and you have to DIY self-manage them yourself. And they're expensive as you scale. That many people can attest right now. And they're actually very cheaper at scale. So what we've seen out there collectively is people start with a cloud warehouse. They're happy until there's more data shows up and the query starts to slow down. They introduce ETLs on the warehouse, which adds more cost. And then when the business decides to do data science or data engineering, usually data scientists will tell you, okay, let's instrument the app, let's try to understand the user behavior. That opens the floodgates for event stream, very high scale data, and which typically are not on the warehouses. They are sent to the lakes. And what you now then see is, data being copied back and forth between these two systems, and leading to a host of different architectural problems. And that's a conversation, a topic for another day. And what what I've seen many people move towards is roughly an architecture like this, where you get your data into a lake and then do the raw data, you ingest it into the lake, you do the ETLs there using a Spark or a Flink or a Hive or a Trino or a Presto or some lake engine. And then you move the data into the warehouse for serving depending on cost performance, right? And this is why that's such an that's what I call an interoperable lakehouse, where you can get unlocked to many engines, not just one engine, and then many frameworks for ETL, many frameworks for querying in an open format, right? So first of all, we live in a multi-engine world. If you take like Flink is optimized for streaming, Spark for batch, Trino or Presto for interactive analysis, that's the world that we live in, at least on the lake, right? And there are many ways to buy all these different engines, right? You can run them yourself, you can buy it from a vendor, you can buy it from a cloud provider. So you really have to plan for an interoperable kind of world. And warehouses typically are not extensible, right? They have to add support for any new format, any new thing that you want them to support. So that's not a good kind of place to be in. And I really hope that changes for the better. And keep the data on the lake in open formats to the lake, because then you can recompute any downstream data when a new framework comes up or a new query engine comes up. You can make it sit on top of that data. So it makes you really much more future proof to do this. And this raw data, or if when the ingest data is usually the most voluminous, right? So it has the most ROI for you to keep it on the lake, and then ETL, and then send a smaller more aggregated, rolled up version of the data into warehouses if you want. And the other thing is, the final point, it creates a single point of entry, right? In the last slide, as you see, a data centering into a system at different speeds through different systems that you have to reconcile. This creates a single point of entry, which means any data quality errors, any mistakes, any kind of errors, your teams can kind of root cause it back to this single entry point. And management, yeah, rewriting all this columnar data is very expensive. So if you want to run clustering, why cluster once for each engine? Just cluster once and then use it across different engines, right? And this avoids data moving costs and copying costs and whatnot. But of course, for this, we need a lot more management. We need the equivalent managed services on the lake for people to be able to do this well without spending months of engineering efforts. And cost-effective ETL. In this model, you can keep the big batch jobs on the lake and then run it using Spark or Flink across thousands of cores, while you can still do small ETLs in the lake or the warehouse, right? And the bigger thing, at least on the Hudi community that we focus on more, is around incremental processing. How do we take these big batch jobs and actually make them more intelligent and incremental? Whether you're on the lake or a warehouse, that's I think where the lot of work is headed towards that. I really hope this was, I added some information to you. And if you want to get in touch with me, here is how you do it. And thank you so much for listening in, and have a great rest of the year ahead.